Hello and welcome to the video. And in this video, I would like to discuss the idea of realizing an integrator using the basic elements we have, which are resistor, inductor, and capacitor. So we have capacitor and inductors in order to integrate either a voltage or a current source. So basically, the behavior of capacitor is to integrate the current across it and give voltage as the output of the integrated current, and in inductors the voltage is integrated and the output is given in the form of current, which is a integrated version of the voltage applied across the inductor. So in practice the inductors are bulky and impractical to make, and due to their very large values which we require, so it is not practical to use an inductor, and thus due to the impracticality of inductors, let's use a capacitor. So while talking about a capacitor, when we have a capacitor and when we apply current IC through it, so we get output as VC, which is basically nothing but 1 by C times the integral of IC dt. And now in our case, what we have is we need the difference between two terminals, and that's basically a input voltage, and we need that voltage to be integrated. So we need our V out to be the integral of that voltage or the voltage difference, and as a capacitor integrates the current, we need a voltage controlled current source, and it will convert the voltage VD into its proportionate current, and that current when passed through a capacitor will get integrated, and as a form of V out will get our output. So let's realize op amp in this manner. So what we have is basically this block where we take the difference between the desired voltage and actual voltage, or basically a negative feedback voltage. So we have our VD over here, which can be applied at a current controlled voltage source, and we will discuss about it in our upcoming videos. But let's say the transconductance of this voltage controlled current source is GM, and when we use a capacitor C and water current generated, which is basically VD times GM, is passed through the capacitor C, so we'll get our output as GM by C times integral I. Basically we have IC, right, and the value of IC is given by VD GM. So basically when we integrate this value, so GM is a constant, so V out will be nothing but GM divided by C times integral of VD dt. So this is the brief idea of realizing an integrator, and as our V out from this equation is basically GM by C times integral VD dt. And previously we saw that our V out was omega u integral VD dt. So we can relate our omega u to GM by C, and that's how we can realize an integrator. So we have our two terminals, and we have a difference of two terminals at the input of our integrator. So that's how it is realized over here. And the current of, let's say, the transconductor of the voltage controlled current source is GM. So the current of GM times VD will flow through this, and we have a capacitor of 1 by SC. So our V out can be given by the current times the impedance due to the capacitor, and this comes out to be GM by SC times the voltage difference VD, which is V1 minus V2. So now we have a structure where we have an integrator or an op amp in negative feedback loop, so that which can be realized like this, and we have our integrator over here, and as we have realized our integrator using a capacitor, so by implementing this, we can basically put our integrator in a negative feedback loop. But we somewhat observe that the produced current, which is IC, is not only flowing through C, but also it flows through the resistive divider, which we made for our negative feedback loop. And as to gain maximum integral, so we need all of our current to flow through the capacitor C, but in reality, we have our resistive divider, and the part of the current also flows through the resistive divider. And so for that sake, we need to isolate this resistive divider from our current. And the best way to do that is a buffer where it will offer infinite input resistance. And thus this current will be isolated from this resistive feedback. So basically a buffer is nothing but which offers an input impedance of infinity and it has a gain of 1. So this is the realization of integrator at block level, let's say, and we will discuss each of its component in real detail in our upcoming videos. So I just wanted to lay an idea or a layman idea about realizing an integrator, which we discussed and put in a negative feedback loop as of now. So so now, as we have realized the integrator, so now that we have realized the op-amp at block level, so we will by before going further and realize it into more details, we have still one point to cover, and which is basically we will study one obvious problem with negative feedback loop or negative feedback amplifier, which is delay. So there can be a delay in a whole process of sensing and integrating the difference between the desired and the actual output. So let's say let's again take the example of a speedometer, and let's say the speedometer tells us the speed with a delay of 5 seconds. So which means that the speed at the current moment is actually of a value which is which it had 5 seconds earlier. So to realize this, we have our desired speed over here, and we have our desired speed over here. We have our actual speed, and what we are doing is basically sensing the actual speed. So let's say simply looking at the speedometer is basically how we know the actual speed. And now we introduce a small delay over here. And in such case, we are currently responding to the speed, which is not the current speed at that instance, but it is the speed which it was 5 seconds ago. So at this moment, what our integrator is responding to, or basically what we are responding to, is not the actual speed at that moment, but the speed which was 5 seconds ago. So let's say we started from rest. So we started from zero velocity, and the actual speed is basically zero, and the desired speed is 50 kilometer per hour. So now we are comparing the desired speed to the actual speed, which was 5 seconds ago. So what I mean by this is starting from zero. So after 5 seconds, the speedometer will start increasing its reading. So our actual speed, so in reality, our actual speed will start increasing from zero only at time zero. But due to the delay, the speedometer will start showing the whatever the actual speed, which is after 5 seconds. So let's say this is our desired speed. Now when actual speed reaches 50 kilometers per hour, the speedometer will still show some smaller value, which was 5 seconds ago, and thus we keep on accelerating, and we will go past um, 50, like we will go past the value of desired value, which was 50 kilometer per hour. And after 5 seconds, we will see that after 5 seconds, our speedometer will give us a value which is past the desired value. So we will see that we have went past 50 kilometers per hour. So we will start uh, decelerating, and again we will end up going lower than 50 kilometers per hour. And after 5 seconds, we'll realize it. So again we will accelerate, and this will go on, and will reach a steady state. But before reaching a steady state, a kind of ripple is being faced due to the delay. So I think I have laid a proper idea of delay and the effect due to delay to our system using this real-time example. And now, like we will reach the desired value, but not smoothly, but by oscillating around the desired value and eventually reach the desired value. So extent of the oscillation basically depends on how much the delay is, as well as it also depends on how faster the integrator was. So basically how faster we took the action based on the actual speed or based on the sensor or the speedometer. So to put this in one picture, so this is what we studied, and as we said that it depends on the value of delay as well as how faster the integrator is. So what do I mean by how faster the integrator is? So I mean by how higher the value of omega u is, because omega u by k is the time constant. So basically higher the value of omega u, higher the response of our integrator is. So basically the one with the red marking is the response to the higher omega u value, and one with the green is basically response to a lower omega u value. And that's how we can say that the delay causes ringing as well as the potential of instability. And we will discuss this in detail in our next video. And that's all for this video. Thank you for watching.